Hello everyone, welcome to the third video of the lecture series. So in this lecture we will again discuss some more problems on quantum mechanics. So let us proceed. So this is the first problem we are going to discuss. So the problem is that consider the motion of a particle along the x-axis in a potential f mod x. So if we draw the potential, what will be its shape? It will be like this. So we have this. So this is the form of the potential. So this is v of x as a function of x, and this, if this is theta, then tan theta will be f. This is the form of the potential in graphical form, and so the Hamiltonian of the particle will be p square by 2m plus f mod x. So this is the Hamiltonian of the particle, and now using the uncertainty principle we have to estimate its ground state energy, and we have to find the factor of f which will appear in the ground state energy. So first of all we have to know what is uncertainty principle. So let us discuss the generalized one. So generalized uncertainty principle. So what is this? It states that suppose we have two observables and we know in quantum mechanics these observables are represented by operator. So A and B are two operators corresponding to these observables. So the generalized uncertainty principle states that sigma A square, sigma B square should be greater than equal to this. So what is sigma A and sigma B? Sigma A and or sigma B, this represents the standard deviation of the observable. So this is standard deviation of observable A. I mean the observable corresponding to the operator A. Similarly, sigma B is the standard deviation of operator B. So, and we know standard deviations are defined by this formula. So this is the generalized uncertainty principle for any two observables. Now, here we have the two canonical conjugate operator x and p. So, and we know that these two conjugate operators share the commutation relation x p is equal to I h cut identity matrix. So using the generalized uncertainty principle we can write sigma x square, sigma p square, it should be greater than equal to 1 by 2i average of this, and let us evaluate this. So this average will be this, and I will be cancelled out, so it will be h cut by 2 whole square. So this is the from uncertainty principle we get. So sigma x, sigma p, it should be greater than equal to h cut by 2. So we can write sigma x. We are denoting this by this formulation. So this is, so for ground state energy, let us assume that the uncertainty relation satisfies the minimum one. That means del x del p is equal to h cut by 2. So for the given problem, we have energy or Hamiltonian of this form. So this is p square by 2m. So let us write this as h, because this is Hamiltonian. So Hamiltonian is plus fx for x greater than 0, and we have p square by 2m minus fx for x less than 0. And since we have to estimate the ground state energy, so for ground state, we can assume that x should be equal to delta x and p should be equal to delta p. So if we assume this, then we have the energy or the Hamiltonian to be of this form. So delta p squared by 2m, and we will have a plus minus f of delta x. Now we can substitute from this relation delta p or delta x. So let us substitute delta p. Delta p is equal to h cut by 2 delta x. So if we substitute this, then we will have Hamiltonian of this form. So it will be 8m delta x squared plus minus f of delta x. So for energy to be minimum, we have the variation of h with respect to delta x. It should be 0 for minimum energy. So if we now evaluate this, we will get delta h delta x. So this is minus 2 h cut square by 8m. We will have delta x cube plus minus f. So this should be equal to 0. So from here we will get that delta x is proportional to f to the power minus 1/3, and there will be constant factor. So that is why I write just the proportionality constant, because we have to find the what is the factor of f. So this factor we have to find. So delta x is proportional to f to the power minus 1/3. So from this we can easily calculate on which factor of f h depends on. So h is h cut square by 8m delta x square. So that means it will be a constant factor. So let us assume that the constant factor is c, and it will be f to the power minus 2/3, and we will have f and delta x. So there will be constant factor and f to the power minus 1/3. So that means h is proportional to the f to the power 2/3. So this is our answer. So we got that the energy, ground state energy, E0, it is proportional to the f to the power 2/3. So this is our required answer. So in this way, using the uncertainty principle, we can estimate on which factor of this proportionality constant this ground state energy depend on. So in problem, there can be any other types of potential form. So what we have to do, just we have to use the uncertainty principle, and we have to keep in mind that for ground state we can assume that the x and p will be just the standard deviation. So in this way we can get this. Okay, so now let's move to the second problem. So the problem states that we have an infinite spiral potential of a particle in a box of size A, and we apply some kind of perturbation. That means its potential is modified as shown in the figure. So here we are applying some perturbation. So, and after applying the perturbation, the energy will also be shifted. So we have to find the energy of the ground state. So compared to the ground state energy before the perturbation was added, how it changes? Like, is it increased by a term of order epsilon? Is it decreased by a term of order epsilon? Or is it increased by a term of order epsilon square, or decreased by order of epsilon square? So so in perturbation theory, we have to first find the first order perturbation. So if there exists a non-zero first order perturbation, so first order perturbation, we know this first order perturbation will be of the order of epsilon, and second order perturbation it will be of the order of epsilon square. So if there exists a non-zero first order perturbation, then we can say that the ground state energy now increase or decrease by order of epsilon. But if the first order perturbation is 0 and the second order perturbation is non-zero, then we can say that the energy now increase or decrease, that we have to find by order of epsilon square. So first let us evaluate the first order perturbation. So we know that the first order perturbation to any state, so for ground state we are denoting this by 1. So for any state, the first order perturbation will be, so this is ground state, this is psi1 square. We have the, so let us denote the perturbation by V. This is a function of x, and we have psi1x. So this is like our first order perturbation correction to the energy. Now if you observe carefully, so in the graph there is no reference point of x is given. So we can assume this is our x equal to 0, and this is our, so basically it will be a by 2 and it will be minus a by 2. So for this kind of potential, we know that for even n, psi is defined as root over 2 by a cos n pi x by a. This is for even n, and psi for odd n is defined as 2 by a sin 2n pi x by a. So this is for even n and this is for odd n. So in both the cases, so here for ground state we have this odd function. So for odd n we will have this as our first, we have our ground state. So if we look at this integration closely, so this psi1 star psi1, this is an even function. So this is an even function, but if we look carefully, this is antisymmetric with respect to the origin. So this integral psi1 star v psi, this integral is a odd integral. So this is an odd integral, and we can say that this should be 0. So it turns out that the energy correction of the first order perturbation is 0. So now we have to evaluate or we have to check if there is a second order perturbation or not. So for second order perturbation, we know that the energy correction is defined by the formula So what are the terms here signify? So basically this is our ground state. This V is our perturbation, as we know. This psi m is excited states. So m cannot be equal to 1. And here E10, this implies the ground state energy of the unperturbed Hamiltonian or free Hamiltonian. And similarly, EM0, this signifies the mth state energy of unperturbed or free Hamiltonian. So here this term is non-zero because here we don't have any even or odd integral concept. But if we look at this term E10 minus EM0, because now we have to find if the energy perturbation increases or decreases. So we have to find the sign of E12. So we have to find its sign. So we have to find if this expression, if it is positive or negative. So now we know that EM0 is greater than E10 because we know that En is defined as n square pi square h cut square by 2m square. So as increases, energy value increases. So this term is less than 0. So we can say that E12 is less than 0. That means we have that the ground state energy before the perturbation was added and after the perturbation was added is decreases by a term of order epsilon square. So our correct answer is this. Now let's move to the third problem. So what does the problem state? So it states that we have a one-dimensional harmonic oscillator and it is in the state as this given. So we know that n is the normalized energy eigenstate with eigenvalue n plus half h cut omega. So we have to calculate the expectation value of the Hamiltonian in the state psi. So let us proceed. So we know what is the form of the expectation value of Hamiltonian. So it is psi h psi. So we have to calculate this. Now, for a one-dimensional harmonic oscillator, we know that Hamiltonian operator is defined as p square by 2m plus half m omega square x square. Now, for harmonic oscillator, it is always handy to do all the expression in terms of raising and lowering operator. So, we have to do the calculations in terms of A and A dragger. So what is the Hamiltonian in terms of A and A dragger? We know from basic harmonic oscillator theory that Hamiltonian is defined as this: h cut omega A dragger A plus half. So you can find this in any standard textbook. So this is the Hamiltonian of a one-dimensional harmonic oscillator in terms of raising and lowering operator. Now, what does this A dagger A operator called? This is called number operator. Why number operator? Because if we apply this to a state n, so it will be, what will be the value? So first this operation will be done. So for that we will have root over n, and it will lower the state n to n minus 1. Now again, if we apply the raising operator, we will have another root n and it will raise to n. So this operator is called number operator because if we apply this on nth state, we have the number n, we have the number of that state, and it will return the same state. So that is why this is called number operator, and it is expressed in this way. So number operator. So we can write Hamiltonian as this: h cut omega number operator plus half. So we have to now calculate this psi h psi. So what is our psi? Psi is given as n0 to infinity 1 by root under n into n. So this is our given wave function. So now we have to evaluate this expression. So let us do the mathematics. So h psi, what will be the value? It will be h cut omega number operator plus half. It will act on this. So h cut omega. So let us do the mathematics. So n 0 to infinity, and we will have 1 by root n. Now if the number operator act on this state, it will give n, and for the second one it will have half. So we will get this, and now if we sandwich this is Hamiltonian between the state, we will get this. So h cut omega m 0 to infinity 1 by root under m. So this is our this wave function, and we have h psi, which is 1 by root under n plus half, and we will have summation over n. So sorry, we have to put the summation here. So let us put the summation here. So n 0 to infinity. So this is our result. So let us simplify this. N m, both are 0 to infinity. We have 1 by root over m into root over n. We have n plus half, and we have m n. Now we know, due to orthonormality condition, this is delta mn. So we will get h cut omega n 0 to infinity 1 by n plus half into 1. So now for the first term, we will have n 0 to infinity and 1 by n minus 1 plus h cut omega by 2 n 0 to infinity 1 by root n. Now we know that this is the expression of exponential. So E is equal to 1 by 0 factorial plus 1 by 1 factorial, 1 by 2 factorial, and so on. So these are the forms which forms you have to remember for for your entrance examination, or it may be given in the question set. So this is the expression of exponential. And what about the first term? So we have n 0 to infinity 1 by n minus 1 factorial. So we can write this as m 1 to infinity 1 by m factorial, where m is n minus 1. So n 0 to infinity, it implies that m has to be from 1 to infinity. So we are getting this. So this is 1 by 1 factorial, 1 by 2 factorial, 1 by 3 factorial, and so on. So what we will do here, we will add 1 by 0 factorial term and also subtract this. So 1 by 2 factorial, 1 by 3 factorial, and all other terms minus 1 by 0 factorial. Now we know 0 factorial is 1. So this term is simply e minus 1. So this is the term we are getting from the first one. So now we have our psi h psi to be h cut omega. So from first term we are getting e minus 1, and from the second term we are getting h cut omega by 2 into e. So if we take 2 common, we will have h cut omega by 2 e plus 2e minus 2. So h cut omega by 2 into 3e minus 2. So we have to find the value of alpha. So alpha we are getting as 3e minus 2. So let us simplify this. We know that e is almost approximately equal to 2.71. So if we do the calculation, it will be roughly equal to almost 8.1 minus 2. So alpha will be almost in the range of 6. So this is the value of alpha. So what is the answer? So answer is alpha almost is equal to 6. Now let us move to the fourth problem. So what does the problem state? So it states that we have the energy eigenstate of a particle in a one-dimensional simple harmonic potential is this, and the particle is initially in the state this. So we have to find the minimum time after which the oscillator will be found in the same state. So first you have to understand the question. So we have to calculate the minimum time after which the oscillator will be found in the same state. That means suppose the time is t. So we will thus, so at time t equal to 0 we have some state, and after time t it will evolve and it will have a state psi t after time t. So suppose that minimum time is t. So after that minimum time the oscillator will be in the same state. That means if we calculate the probability of collapsing psi at time t with psi at time t equal to 0, then the probability must be 1. So that is the catch. So we can easily calculate this. So let us proceed. So we have psi at t equal to 0 as 1 by root 2, 0, 1. So since these are the energy eigenstate, we can write psi at a finite time to be 1 by root 2 e to the power minus I E0t by h cut. Let us denote the ground state energy by E0. So E0t by h cut 0, and we will have e to the power minus I E1t by h cat, and it will be 1. Now E0 we know h cut omega by 2, and E1 we know to be 3 by 2 h cut omega. So psi at t and psi at t equal to 0, we have to find its this one. So it will be 1 by 4. We will have e to the power I e0 t by h cut 0, e to the power I e1 t by h cut 1. So this is psi t, and we have psi 0, which is 0 plus 1. So this its mod value. So evaluate this expression. We have done in a previous problem the similar type of problem. So let me do the calculation first. It will be I e0 t by h cut, and we will have e to the power I e1 t by h cut, and its mod value. That means we will have, so we have done this in previous problem, so I am just writing the value. You can go back to the video and watch it. So it will be 2 cosine of e0 minus e1 t by h cut. So it will be half 1 plus, and e0 minus e1 difference is h cut omega, and so h cut will be cancelled out. So we have just omega t. Yeah, so this should be 1. So 1 plus cosine of omega t, this should be 2, and omega t should be 2 pi. So from here we can get, so this is minimum time. So if we so after, in place of 2 pi, it can have 4 pi, 6 pi, 8 pi. So these are the later times at which we will have the we will have the oscillator to be in the same state. But for minimum time, we are replacing this by 2 pi. So the time will be 2 pi by omega. So the correct answer is D, 2 pi by omega. So this is the answer. So that means this is the minimum time after which the oscillator will be found in the same state. So that part of the question you have to understand. Found in the same state means, so after time t, the whatever the state it is, the probability of collapsing it with the initial state will be 1. So from that you can calculate this by simple trigonometric formulas. Okay, so that's it for the third video. So I will meet on the next one.